Today, we are diving into the story of magnetars, the absolute strongest magnetic objects in the entire universe. These are not black holes that swallow light, nor are they ordinary neutron stars that spin and pulse like cosmic lighthouses. Magnetars are a rare class of neutron stars, built for one thing, generating magnetic fields so intense they can tear atoms apart, warp the fabric of space-time around them, and release explosions so bright they briefly outshine every other star in the Milky Way combined. If you have ever wondered what happens when nature turns magnetism up to a level no human machine can ever copy, you are about to find out. To understand magnetars, we first must understand where they come from. Every magnetar begins its life as a massive star far bigger than our Sun, between 20 and 40 times the Sun's mass. These stars live fast and die young, burning through their nuclear fuel in just a few million years, a blink of an eye in cosmic time. When their core runs out of fuel, gravity takes over, and the star collapses inward in a fraction of a second. The outer layers crash down at nearly a quarter of the speed of light, and rebound in a catastrophic explosion called a supernova. For a brief moment, this supernova can shine brighter than an entire galaxy, but what is left behind is not a black hole, not always. Instead, the core crushes into a neutron star, a sphere only 12 to 20 miles wide, roughly the size of a large city, yet packing more mass than our entire Sunday. A single teaspoon of neutron star material would weigh as much as all the humans on Earth put together. Density does not even begin to describe this state of matter. But most neutron stars are not magnetars. Only about 1 in every 100 neutron stars becomes a magnetar, making them one of the rarest objects in the Milky Way. What makes them different? The answer lies in the first few seconds after the core collapses. As the infant neutron star forms, it spins insanely fast, up to 1,000 rotations per second, while churning with superheated, turbulent plasma inside. This combination of extreme rotation and chaotic convection creates a cosmic dynamo effect, amplifying the star's magnetic field to levels that are almost impossible to comprehend. By the time the supernova fades, this newborn magnetar has a magnetic field that reaches 10 to the power of 14 to 10 to the power of 15 Gauss. Let us put that number into perspective so you can truly grasp its power. Earth's magnetic field, which protects us from solar wind and guides compass needles, is about 0.5 Gauss. A standard refrigerator magnet is roughly 100 Gauss. A hospital MRI machine, one of the strongest magnets we build on Earth, tops out at about 10,000 Gauss. A typical radio pulsar, already an intensely magnetic neutron star, has a field of 10 to the power of 12 Gauss. A magnetar, it hits 1,000,000 Gauss, a quadrillion times stronger than Earth's magnetic field. If a magnetar were placed as close as the moon, its magnetic field would erase every credit card, hard drive, and magnetic storage device on Earth. It would strip away our atmosphere, tear apart our cells at the atomic level, and end all life in an instant. This is not just strong magnetism. This is a force that rewrites the rules of physics. The story of how we discovered magnetars is one of the most thrilling detective tales in modern astronomy. For decades, astronomers detected strange repeating bursts of soft gamma rays coming from deep space, but they had no idea what caused them. They called these sources soft gamma repeaters, or SCRS. The breakthrough came on March 5, 1979, when several space probes, including NASA's Venera and Helios satellites, were hit by an enormous blast of high-energy radiation. The signal was so intense that it saturated the detectors on every spacecraft that saw it. Scientists traced the burst back to a supernova remnant in the Large Magellanic Cloud, a small satellite galaxy of the Milky Way. At the time, no one could explain such a violent, repeating explosion. It was not a normal supernova, not a gamma-ray burst, and not a pulsar. For years, the mystery remained unsolved. Then, in 1992, two astrophysicists, Robert Duncan and Christopher Thompson, proposed a radical new idea. These strange bursts were coming from neutron stars with unimaginably strong magnetic fields, magnetars. At first, many astronomers were skeptical. A magnetic field that strong seemed too far-fetched, too extreme to be real. But over the next 10 years, evidence piled up. In 1998, astronomer Krisa Kuvliel led a team that measured the slowdown of one famous SCAR 1806-20 and calculated that its magnetic field had to be nearly 10 to the power of 15 Gauss. That single measurement convinced the scientific community that magnetars were real. The mystery of soft gamma repeaters was solved. They were magnetars, the universe's ultimate magnets. Let us talk about SGR 1806-20, the most famous magnetar ever found, and the strongest magnetic object ever observed. Located about 42,000 light-years from Earth on the far side of the Milky Way, in the constellation Sagittarius, this tiny, city-sized star rotates every 7.5 seconds and carries a magnetic field that defies belief. On December 27, 2004, CR 1806-20 unleashed a monster explosion, a starquake, so powerful, it released more energy in 0.2 seconds than the Sun releases in 250,000 years. The blast wave of gamma rays and X-rays traveled across space and slammed into Earth's upper atmosphere. It ionized our atmosphere, disrupted radio signals, and was detected by every major space telescope in operation. Even from 42,000 light-years away, this Magnetar-S explosion was bright enough to temporarily blind some satellite sensors. What caused this unimaginable blast? A starquake on Earth. Earthquakes happen when tectonic plates shift. On a magnetar, the crust is an ultra-rigid layer of densely packed neutrons, locked into place by the star's incredible gravity. But the magnetic field inside is so strong that it pushes and twists the crust until it cracks. When the crust breaks and rearranges itself, the magnetic field snaps and reconnects, releasing a flood of high-energy radiation. This is a starquake, and it is one of the most violent events in the universe. Imagine a quake on a star that can shake an object so dense it would crush any known material instantly. That is the power of a magnetar. Magnetars do not just explode. They change the space around them in ways no other object can. In the presence of a magnetar-S field, atoms are stretched into long, thin cylinders instead of their usual spherical shape. Electrons are ripped away from nuclei and matter. As we know, it cannot exist. Even the vacuum of empty space becomes polarized and bends light in weird, unpredictable ways. These conditions are so extreme that they cannot be replicated in any laboratory on Earth. Magnetars are our only natural laboratory for studying physics under the most intense magnetic forces possible. They help us test theories of quantum electrodynamics, nuclear physics, and general relativity in ways no experiment ever could. Every time we observe a magnetar burst or measure its field, we learn something completely new about how the universe works at its most fundamental level. You might wonder how long these cosmic powerhouses stay active. Unlike ordinary neutron stars, which can spin and shine for billions of years, magnetars live fast and fade young. Their ultra-strong magnetic fields decay over time, losing their energy in roughly 10,000 years. After that, they quiet down, stop producing giant bursts, and turn into ordinary inactive neutron stars. This short lifespan explains why we see so few magnetars. Today, only about 30 confirmed ones in the entire Milky Way. But astronomers estimate there are more than 30 million dead quiet magnetars scattered across our galaxy, invisible to our telescopes until they might flare again. These ghostly remnants are silent witnesses to the universe's most magnetic moments. NASA and other space agencies have spent decades studying magnetars, using some of our most advanced telescopes. The Fermi Gamma Ray Space Telescope scans the entire sky for gamma ray bursts, catching magnetar flares as they happen. The Chandra X-ray Observatory and ESA SXM Newton Telescope peer into the hot, high-energy environments around magnetars, mapping their magnetic fields and measuring their temperatures. The James Webb Space Telescope, with its infrared vision, has begun studying magnetars embedded in dense nebulas, helping us understand how they form and how their explosions affect their surrounding star-forming regions. Every new observation brings us closer to answering the biggest questions about magnetars. How exactly do their dynamos create such strong fields? Do they cause fast radio bursts? One of astronomy's newest mysteries. Could magnetars be linked to superluminous supernovas that shine brighter than any normal stellar explosion? Magnetars are still full of secrets, and every discovery opens a new door to understanding the universe's most extreme physics. It is easy to think of magnetars as distant, terrifying monsters that have nothing to do with us. But that is not true. Magnetars play a quiet but critical role in shaping the cosmos. Their explosions spread heavy elements across space elements that eventually form planets, stars, and even the building blocks of life. Their magnetic fields influence the evolution of galaxies, compressing gas clouds and triggering new waves of star formation. They teach us about the limits of matter and energy, pushing the boundaries of human knowledge further every single day. When we study magnetars, we are not just studying weird stars. We are studying the fundamental rules that govern everything in existence. The universe is full of wonders that we are only beginning to discover. Black holes, neutron stars, dark matter, dark energy, all of these remind us how small we are, but also how brave we are to look up and try to understand. Magnetars stand at the peak of cosmic extremity, tiny, dense magnetic powerhouses that turn physics upside down. They are proof that the universe is not just calm and predictable. It is wild, violent, and infinitely more powerful than we can imagine. As we keep building better telescopes, launching more missions, and staring deeper into space, we will find more magnetars, unlock more secrets, and keep rewriting the story of the cosmos. Please like, comment, share, and subscribe to the channel.